Hi, my name is Trey Clark. I'm a senior AI and ML solutions architect with AWS. In this video, I'm going to take you through a quick hands-on tutorial using SageMaker Data Wrangler. This is Amazon's low-code, no-code service for preprocessing your datasets for machine learning. And in this tutorial, I'm going to quickly run you through creating a Data Wrangler flow, loading a dataset into Data Wrangler, performing some data exploration. I'll show you some of the built-in feature transformations. I'll show you how you might use a custom feature transformation, some of the reporting tools, and then finally, we're going to export the data for future use. For this tutorial, I found the dataset on Kaggle. This is the stroke prediction dataset. There are 11 clinical features. There's a little bit about them here that's not super important for us, but there's an ID, there's gender, there's age, there's whether or not the patient had hypertension or heart disease, etc. And then finally, there's the stroke column, which is whether or not the patient experienced a stroke. So this is the data set we'll use, and we just need to place it into S3. So we'll download it. I've already done this, and then we'll upload it to S3. I have also already done that. And so just to show you, that it is in my bucket. And here we go. We have healthcare dataset, stroke data, and it's a .csv. So with this, our plan is now to load SageMaker and then Data Wrangler, and then we'll load this dataset in. Okay, I'll just jump into this domain, and I'll launch the default user. And that will load right up. Okay, so now we're at our studio home. Oh, as a quick aside, recently, as of this video, there's been a change in the UI for Studio. So don't be thrown off if your interface is slightly different. All of the commands will be the same. You just have to start Data Wrangler from your SageMaker resources panel, which will be an orange icon here on your left lower panel. But for us, we're going to look at data and click on Data Wrangler. This will load up our Data Wrangler tab. Right now it shows that I have one flow already here. This was just me ensuring everything worked correctly. But now we want to load a new one. So you go to File and go to New, and you just want to launch a new Data Wrangler flow. And so that will spin up in a few seconds. Okay. Data Wrangler has finished initializing. It didn't take too long. It was roughly 60 seconds. But again, there was no reason for me to make you all wait through that. At this point, we can now import our data or use sample data. Since we already have our data together, let's pull that in. We have a number of options for data sources. We'll be using S3 because that's where we placed our data, but Athena, Redshift, Databricks, any of these you're free to use and may do a video about those in the future as well. Also recently, there's been the addition of 42 custom data sources or application specific data sources. And these can be accessed through Amazon AppSync. So that's really cool. We'll play around with that definitely. And at this stage, we'll click S3. We'll go through the Explorer-like interface and find our dataset. We'll click it there. And so once we've clicked it, below we'll have the first 100 rows or so imported, and we just want to make sure our features are there. So we have ID, we have gender, age, hypertension. Okay, everything looks like it's there. We have whether or not the person experienced a stroke. And in our right-hand panel, we'll have just some inferred data from Data Wrangler. So this is a CSV. The first row is the header. It's comma delimited. And then it shows us the sampling options. So Data Wrangler actually acts on a sample of your data. You have the choice of trying to load it all in, but for really large data sets, you can imagine how cumbersome that becomes. But for classification, my default is to use stratified sampling. I just want to keep the ratio of my target column similar to the full data set. Okay. And with that, we now click import. And while that's happening, I'll just close that panel. Okay, so it's loaded in our sample. We're good to go. There's been some shuffling as well, which I appreciate. At this point, the first thing you'll usually want to do, which we don't want to do, or we don't have to do in this case, is change our data types. So Data Wrangler will infer the data types, and for the most part, it'll be correct. But there might be a few cases where you want something to be considered a string that was considered an integer or so on. In this case, this all looks good, and so we should be good to go. So we don't have to change anything there, but we can. Or something is a date. Let's do some data exploration. Right? So that if we were preparing this data set to be used for some machine learning, we might do some data analysis first. If we go to our analysis tab, the first thing I will start with is a data quality and insights report. And what this report is designed to do is just look at your target column, your target variable, and whether the problem is classification or regression. And it'll create a report just sort of giving you some statistics about your data set, as well as noting any sort of anomalous points in your data set and letting you decide how to use them. It'll also perform sort of a quick model, which is designed to sort of estimate what your performance would be if you trained a model on that data set right away. And that was pretty quick. It's not fully done, but we'll start with some of the dataset statistics. There are 12 features. We already knew that. There are only 5,100 rows. Okay, good to know. There is some missing data here, less than 1%, but still exists. And we don't have any duplicate rows. And then we have a breakdown of our feature types. Okay. From this point, it tells us about any high priority warnings. It doesn't look like it detected any. It didn't detect any duplicate rows. And then it shows us our anomalous samples. So these anomalous samples are found using an isolation forest algorithm, where if we look at our anomaly score, effectively anything negative we consider an outlier, and then it shows us the point or the points that it considered anomalous. And from this stage, we can determine what we do with them. One option could be remove them. Another option is do nothing. Or we could edit them sort of in the extreme case if we think that there's a data collection issue. But in this case, just sort of scanning it, looks like there's some sort of bias going on in the age, and that everyone here, save maybe 57, is fairly elderly. And also everyone here sort of has experienced a stroke. So that's interesting. I'm not sure if we're going to do anything with that in this time around, but we could remove these columns if we'd like. We do have the ID, and we can do that with Data Wrangler. Next, it'll show us the breakdown of our target column. And this is just to show us any imbalance or if there's some validity issues, some data quality issues there. In this case, it does appear that our frequency of non-stroke patients heavily outweighs our frequency of patients that experience stroke. That's not surprising from a data collection point, but we will probably want to do some balancing of our data set. And we can do that within Data Wrangler. I'll probably save that towards the end when we're wrapping everything up. And yes, that will be something good to know. This is also sort of good to see, and this is one of the reasons why we chose stratified sampling, is just to say, this is probably similar to our distribution for the entire data set, versus some of the other sampling methods that could have been skewed one way or the other. Finally, it shows us a quick model. So if we were to build a model, with the data set that we had right then and there, what sort of performance might we expect? And because this data set is so heavily skewed, as you see, our accuracy is high for the training and validation. But if we were to look at F1, it's pretty poor. This is further broken down in this classification report here, just sort of showing that our F1 score for the stroke victims is much lower than in the case of our non-stroke victims. And we can see the support here, so roughly 1,000 to 50. So we'll definitely want to do some balancing there. Okay, good information. We'll keep that in mind as we're moving forward. And now we want to click on data flow, which will take us to sort of our pipeline view of our process, or our process view. And in this case, it's broken up into steps. So our first step was just loading our data from S3. Our next step, we're looking at data types or inferring data types in this case. And now we've just performed a data quality and insights report, or just generated a data quality and insights report. At this stage, we want to do some more data exploration. This is the quality report. It's got me interested in some of the features. So let's perform some analysis. And there are a number of, again, a number of charts and reports that you can make. I'm going to look at some bar plots. I guess first for gender, that's our first feature. And there's an option to color. So essentially to split this up by another column, since we have a target variable, I want to see if there's a difference in the distribution for when accounting for the target variable. And for this, we're always going to preview first. Okay, so we have roughly 3,000 female, 2,000 male, and there's an other column that seems too small for me to see the exact the approximate value, but it's sort of very small. So I wasn't expecting that. That is good to know, and something we'll look into. And if we look at the distribution, the breakdown of patients that experienced a stroke. So this is the dark blue versus patients that didn't experience a stroke. We know there's an imbalance, but there doesn't necessarily seem to be an imbalance across male and female. As an additional option, we can also select a facet column, which just splits this up into multiple bar plots or histograms based on another feature. So we can look at work type, let's say, and preview that. And it'll break it down by the work type. So this is male and female and other for people that had a government job, for people that had never worked, and and so on and so forth. And so we can look at this and sort of determine if there are any imbalances here, or things that we might want to be aware of. Okay, this all looks. There doesn't seem to be anything crazy, although there do seem to be more male children than female children. So it's something to know. And with that, let's save this. And so it's been added to our set of analysis. And if we look at our data flow, there's now a new point, and that's that histogram for gender that we made. And so we can add another piece for the next feature. Let's do age. So we'll do a proper histogram. We'll use age. Let's also color by target column. And let's preview. Okay, so this seems roughly in line, right? So they're children. We have more people that are older as part of this study or part of this data collection, which seems reasonable. There do seem to be proportionally less children that experience a stroke, which is what we would expect. there are a few people in the 80 to 90 range. So, okay. The with maybe proportionally more stroke incidents than in previous age ranges, but all of this is good to know. I'm happy that we have this. Uh, we could also split this by a facet just to make sure, just as a sanity check. So let's do maybe people with heart disease. I would imagine very few children have heart disease, or I hope. Right. And so here's the distribution of people that have never had heart disease. It looks roughly like our population, a little shorter on the tail. And then if we look at the population of people with heart disease, they're effectively no one under 40, which is good and expected. And so we can save this. And looking at our data flow, we now have these three analysis sets, and you can do this for all of them. I'm not going to do it for every feature because I think you get the idea, but one more analysis bit that I will do is look at feature correlations. And this will just do, as you might expect, a sort of correlation between each, pairwise correlation between features. Let's preview this, and it shouldn't take too long, but I've said that before and been corrected by a Data Wrangler. Okay, so that processing completed. It took roughly 5 to 10 minutes, less than 10 minutes, but maybe more than 5. And what we have here is a general explanation of what the feature correlation is showing you, or what feature correlation is, how to interpret it, and then we'll have our top uh, top 20 correlations. So in this case, age and work type were most highly correlated, roughly 0.7. That sort of makes sense. If you're young, you have a certain job, which is no job, and if you're older, you probably have there's a different distribution of jobs. I can see how that could be correlated. Work type and age, so the same thing, just reversed. And then ever married in age, which also makes sense, right? At least in this data set, I hope there are no children that are married, or no really young people that are married, or I would expect none to be married. And then as you're older, more likely to be married. So we have these. If we scroll down, we also have a correlation matrix. So this is just a heat map of what you see above, but for all of our features, and we can sort of see the same, so the what we saw above, except visually. So in case of age and ever married and work type, these are correlated. Something that I guess makes sense is also BMI, or body mass index, is correlated to if you're ever married slightly, and then correlated to if your work type, which does make sense as well. So we have these feature correlations before we've done any transformations. And with that, oops, we should be able to save, or I guess I already saved it. And if we head back out to our flow, we can see, right, we have our feature correlation there. And now we have these analysis stages. And although we could do more, I'm not going to here because I think you get the point. And now we're ready to start transforming our data. So that takes us back to this screen where we have sort of our S3 source step and then our data type step. And what we're going to do is add a step. And before doing that, let's just look at the features we want to deal with. So we have gender, which is sort of male, female, and other, that I still need to look into, but let's hold off on that one because we may just need to remove other if it's really small, but and then turn this into a binary variable. But we want to turn these features into numerics. We have age here. This is continuous in a sense. I guess it is discrete, but really continuous. And let's maybe bend this, right? Because the as we've seen, there is a correlation among age. The child stage is maybe 0 to 18. There's the young adult stage, 18 to 25, and then sort of so on. And what we can do is turn this into a bin, and that for that transformation, we're actually going to make a custom transformation. And when you click custom transformation, you can give this a name. I'm going to call it age binning. But you're given sort of a kernel to use. And you can use PySpark, Pandas, a Python user-defined function, or PySpark again, but SQL. And I'm going to use Pandas for convenience. It'll give you a warning because for you to perform sort of a Pandas operation, the dataset needs to be in memory, but that won't be a problem for us. And when you're making a custom function, essentially think of it as a Python script. So you have access to df, and that is your data frame. That is the data frame we have here. But anything else you want to use, you need to just make sure that you import for it. So in this case, we don't really have to do any other imports, although we could. We just really want to update this. We just want to make a new column that will be sort of a between. It will be a variable that labels what age the child is in. And so this is ordinal, so we'll keep it ordinal. We can keep it in the same column. And here we're just going to say from 0 to 18, and we're going to include both ends. We'll call the bin age 0. We'll do this also from, let's say, 18 to 25, and we'll close it on the right. And we'll say that this is 1. And just because I don't, well, okay, so let's do 25 to 100 space. You can make more, your choice how you deal with this, but we'll call this 2, and these will be our super adults, young adults, and then super adults. And with this, we've now created this new bin. We can preview, just make sure we don't have any errors, which I hope we don't. And we should see a column that's age bin at the end. Yep. And there we go. And so these are all 2s. Let me just make sure they're over 25. Yeah, and they certainly are. Okay. So we've now added this column. And just this is now the integerized or binarized version, quantized, of age. And so we'll add this. Now it's added. And as sort of another sanity check, let's make a figure for it. So we go to analysis. We want to make a histogram for age bin. And we should see that variable show up, age bin. We can still color by stroke. That seems fine. And here we go. And it looks like the only people that have strokes are super adults. We'll see how useful this is to the model, but let's certainly save this. So something to note, if we look at our data flow, is that at this stage, we perform some analysis on the data, and we have these offshoots. Here, we just performed our age binning. And on the age binned data, we then performed another analysis. And so that analysis lives off of this stage. And so that's just something to keep in mind. Your analysis is based on whatever data transformation stage you're at currently. Oops. Okay. Excellent. So let's do another transformation. Again, I'll leave gender alone for now. Hypertension is already binary. We don't need to do anything with that. Heart disease is already binary. We don't need to do anything with that. Ever married. And so I'm pretty sure ever married is binary, but just in case it's not, let's perform some analysis. married, and then we'll preview this. Yes, excellent. So it's just no and yes. So what we're going to do, so I'll save that and then go back to data. So let's add a step that then turns this into a binary variable. So there isn't a sort of fixed transformation that just says binarize, but really what we're doing is encoding a categorical variable. So we can encode this categorical variable, and now in this case, since there are only two values, we can do an ordinal encode, and this will put it all in the same column. And we want to use ever married. Okay, and we can now preview this. And it should update our ever married variable. Now it's a float instead of a string, and it'll be 0 in the case of married versus 1 if not married. Okay, that looks good. That's a number. Let's continue on. Oops. Let's look at our other features. So I'll do this one more time. I won't do this anymore, but so now we want to deal with work type. So let's get a feel for what type looks like. And just see, I'll also color it because I didn't the last one. Okay, there are 5 work types. There's some distribution of whether or not the person experienced a stroke. Okay, understood. It's not too many. And just to show you again, because we performed another transformation, now this analysis is an offshoot of this transformation. And so let's add a transformation where we process this column. And these are categorical variables, so let's one-hot encode those. And we'll go back to encode categorical. And instead of using an ordinal encode, we'll use a one-hot encode. And you have a number of options here. So first I'll choose the column. Let's do work type. Work type, you can choose multiple columns. So I'll also do residence type. In the same process, we'll just assume that this will be fairly easy. It is sort of binary, but I'm not going to deal with that for now. We'll just make it a one-hot encoding for both of these just to show that you can do multiple variables. And for invalids, we'll keep them. No, let's keep them. And then for our output style, so you have two options here. You can make them a vector, which will place them in the same column, but now it'll just be a vector representation in that column, or you can make them columns. And so the making them columns is my preferred method, but that's really only valid if you only have a few categories, right? You don't want to go more than 100 or so. You don't want to add more than 100 columns here. This works for us. We can preview. Okay, and so it's now removed those old columns, the categorical columns, and if we scroll to the end, what we have is work type underscore what that value was, and right, we have our one-hot encoding, and this just expands all the way out. Okay, that all is good. Those are now numbers. Most things are numbers, except for smoking status. And I'll actually do something a little bit different here. So first I'll add this. Now let's look at smoking status. So we have never smoked, smokes, formerly smoked. There's an unknown here, which makes me a little nervous. So let's just check that. Okay, there's only 4. Okay, so my standard approach would just be we can one-hot encode this. I'm actually going to do something different because there sort of is an ordinal structure here, just to show you something else with a custom transformation. I'll save this and go back to data. and we'll add a step, and this will be a custom transform. And for this, it will be smoking ordinal. And we'll use pandas again. And for this, I'm going to make a mapping. And my mapping will be, if you never smoked, that's sort of the lowest value. If it's unknown, that's worse than never having smoked, but is I'll say is better than formerly smoking. So that's 1. And then formerly smoking, and then smokes currently as the sort of the furthest value. And I need to now map this. And so my smoking status will then be mapped with this mapping. So let's preview. And just make sure everything turned out okay. Okay, so we have our numbers there. So that column's been made numerical. We'll add it. We're roughly in good shape. So now gender. Let me. What's the easiest way to deal with this? So for the purposes of this, I'm actually going to drop this column. So I'm going to add a step, or sorry, drop the row that contain other. And then we'll check what sort of damage we've done. Other. This is just for the example. And again, we're just going to make our data frame. Where data frame. Oh, I guess I could use dot location as well, but we'll do it this way. And we'll preview that. Make sure we're, whoops. Well, okay. Yes, and that's what we wanted to do. We could also then binarize the values here, and let's just do them all in one. So we'll do a mapping. It will be 0. No, will be 1. BF equals. Let's just override it. Let's just make sure this is okay. Okay, so we've changed gender. It's now ordinal. Now binary, and I think we've taken care of all of our variables. And so we'll add this. One thing that is sort of standing out, everything's effectively binary, save for these 3 columns: age, glucose level, and BMI. So in dealing with that, let's normalize those. If we scroll down our list, we have a process numeric transformation, and we can scale values. You have your choice for a number of scalars. Standard scalar is fine for this, and we'll just choose our variables. So let's choose age. Oh, it's in float. BMI, and then average glucose level. We can also center it. Your choice. I won't here, but you can. Okay, and so now these are normalized. Uh, eh, Still slightly out of the range of some of the binary variables, but that seemed fine. Good enough for this example. And now let's add this. And we're almost done. There's one other thing we want to do. So there's this ID column. Let's remove this so we just have our data. So we can add that step. And we can manage columns. And we can drop a column. And in this case, we will just drop ID. Preview it. Seems fine, it's gone. We'll add it. And finally, for some of the SageMaker built-in algorithms that we may use after this, they expect the target variable to be the first in the dataset, for CSVs at least. And so let's move this column. Again, that'll be manage columns. And let's, well, not drop, let's move the column to the start. And that'll be the stroke column. So we'll preview it. Okay, it's there. We'll add it. Great. Now if we're looking at our flow, this is what we have right now. And we're ready to perform some final analysis here. So we'll head back to our analysis. A couple of things we can do. Let's first do the data quality and insights report. Again, our target variable is still stroke, it's still classification. Let's see if anything's changed. And I just remembered that I said we were going to balance our data, which we'll do right after this. Okay, that's completed. Some anomalous business here, which I think is effectively the same features. Oh no, there. Oh wait, sorry. That column's in the front now. Which at least seem to be mostly the points we were having before, right? We haven't changed anything really substantively about our data set. So if those points seemed like anomalies before, they're still anomalies. Still not going to do anything with them. We still have our imbalance, and let's see, and we still have the same performance. So let's head back out and do some balancing. So I'll just zoom in so we know where we are. So here's our data quality report that we just made. Let's add a transform. We're going to add a step, and we are going to balance our data. And our target column is stroke, and that's what we're aiming to balance. And our desired ratio is 1, so we want it to be roughly 50% of our data set, and we're going to use SMOTE for that. We have a number of neighbors that we choose here. I'll leave this here. Just allow it to work its magic. There's a lot of data to replicate. This may take a bit. So we have an error. Great. Doesn't currently support missing values. So let's go back. And first, so we have a choice. We can drop the missing rows, or we can do some imputation. Let me just see where, there we go, handle missing. So we have our choice. We can impute, we can fill it with the value that we choose, or we can drop them. Let's use impute. This can take some time, but luckily for us, we don't have a very large data set. The column type will be numeric, and our column, if I remember correctly, was BMI. Let's just see. Yep, BMI. Um, oh, okay, never mind. These will run pretty quickly. So let's just choose median. Let's preview that. Let's check the BMI column. And now we have points there. Okay, great. Let's add that. And then now let's balance our data set. So we'll set the target variable to stroke, still mode, still 50%, still 5. Let's see. Okay, not too bad. The we should see a bunch more ones. We're not going to be able to see it here, but we can if we add this and then add some analysis. And again, we're going to do our data quality report on the stroke column, and this is for classification. And now that this may take a bit longer, but so we can already see, right? We've increased the number of rows we have because we effectively not doubled, but almost doubled our data set size. Okay, so we have a target leakage warning. The feature age protects the target extremely well on its own. A feature this predictive often indicates an error card target leakage. Excellent that it's showing us this. I'll disagree here. And we will move forward. Let's see how easy the task is when we get down to results. Again, we still have our anomalous results. Our now frequency is 50-50, which is good. And our quick model is now performing much better. We look at our F1 score. And if we look at the performance for precision and recall and F1 for our stroke class, it is now in line with that of our other class. And so it did say something about this feature being too predictive. The way we can test that, oops, oh, okay, so we have more information, it's confusion matrix, and then we have our feature summary. Seems like in this case, age performs really well. Although, if we look at the feature importance, I would say BMI is pretty important as well as smoking status and sort of so on. And yes, there's a warning here. Well, we can do a couple of things there. So again, this is that target leakage question. So there's a lot of useful information here that you definitely can go through. I won't go through it all. It sort of is a breakdown of the features and how they sort of add to the model and to the prediction. But we're now at a stage where, oops, if we head back out, we've now added an imputation to fill in missing variables. We've added smote to oversample, and we're sort of at the stage where we've done our data quality and insights report. I'll just show you one other report, which is a bias report. And in this case, we're going to look at bias for a particular variable. I'll look at our target and our value of 1. And we can select a column to analyze. So this is relative to our target. Is there a variable that is biased? I'll choose H here. That's not what the target leakage question was about, but it's asking me for threshold. Now I wish I'd kept them as, okay. Let's say we don't choose that. Let's see what happens. There are some of the bias metrics that you can choose, or you can just leave the default one selected. And let's see if we can do this. Okay. Let's use age, and let's see if we leave it blank, what will happen. Okay. All right, let's use 0 and see what happens. Okay, and so we have our sort of class imbalance metric. Is there an imbalance in class? Which we sort of saw. 0 would probably be putting this closer to 50, which would bias things a bit. The some of the metrics that we're really interested in, the difference in positive proportions, which we knew had sort of an imbalance, right? Again, remember, children, at least from our histogram, seemed very unlikely to uh, suffer a stroke, and this being close to -1 is effectively saying the lower class is very unlikely to see, sorry, the lower values are very unlikely to see a stroke, a positive prediction. But then if we look at our Jensen-Shannon divergence, which is discussed here, the larger, the sort of more biased, we're seeing a value very close to 0. So that's a good sign. We'll save this here. And then the last thing we'll do is create a new analysis, and that will just be our quick model again. So separate from the data quality and insights report, we'll use this model here just to show you the difference. And let's see if I can choose a column. Let's try again. Okay, there we go. So our labels the stroke column, we'll predict preview. And this should take a few seconds. Okay, and so now this is performed a training of the model. So it used a random forest, so it gives you a bit of information about what it's doing. Using a random forest with some of the default hyperparameters, we were able to achieve an F1 score of 0.81 on a test set. And here are some of the feature importances. We already knew age was an important feature. Here it is. It is still very important. And then we have some of the other features. So this is if you want sort of a specific model. The data insights is using sort of a different model there. And so I like to get both just to see some of the differences. So 0.81 is pretty good. I think we'll say it's good enough for us here. We'll save this. Look at our data flow. We we've done some steps, although I would say we've done some steps without having to do a lot of coding and without a lot of hassle. Next, we actually want to export this so that we can use it later. And so if we click on the last transformation we performed, we can export. And there are a number of options. We're going to export it back into S3 because that's sort of the simplest thing that I wanted to show here, but there are a number of other options. So if you want to add this to a pipeline, we can definitely do that. Or if you want to add this to SageMaker Feature Store, which is effectively a database for your process data, you can also add there. Oops. If you also just want the Python code itself, you have that option as well. We're going to choose S3 and leave the others to feature videos. So what this will do is generate a notebook for you that's whose only function is just designed to process your data in full and then output your data into S3. So it's starting the kernel for that. Shouldn't take too long. And we're back. So roughly 60 seconds, not too long. Again, not worth it to make you all wait. And here we have a notebook. It's designed to just export to process the full data set and export it into S3. It'll export it into the same S3 that we pull that data from, although you can change some of these options here, especially if you have a different data set you wanted to process, or if you want it to pull from a different destination, and if you want to change where it will output that data. So here it'll output it into our default bucket, and we'll show that. So you don't have to do anything else. From here, you can just restart and run all, or just run all. I'm very used to restarting the kernel and running all. And this will chug along. And I will time it, but will not keep the video running for that, but we'll pause it and come back.